modern stuff on long-time behaviors and sampling processes. But today, I've decided to pick on a couple of topics.
Sorry, Des, are you planning to use the Blackboard?
Yes, I'm going to have mostly slides and partly Blackboard. Just trying to find the page. There we go. Page down.
There's also a clicker. I don't know.
Yes, I think I've copied strings. So the classic numerical analysis perspective, looking at trajectories, we tend to think of what's called strong convergence. There's also something called weak convergence, which I'll mention briefly. I'll just sketch out the proof that's typically given for the strong convergence of a basic numerical method for an SDE. And the second topic will be linear stability. So this is a long time behavior topic. Fit in with some of the sampling talks that come later this week. As I said, this is based on a couple of chapters from the book. The book does have exercises. So some of the gaps today are exercises in the book, and there are solutions online as well to those exercises. There's also code, MATLAB code associated with the book, and lots of references. So although the book isn't giving you all the technical details, and neither is the talk today, there are references there that you can follow up if you really are interested in rigorous proofs of these results. So we're not trying to be rigorous, we're just trying to give the basic ideas. And I'll spend a little bit of time on the Blackboard just setting up the notation and some of the ideas. And we seem to have the Japanese fantastic chalk. I never used this before, but this is a very expensive piece of chalk apparently. I hope you appreciate the quality. So I'll just focus on scalar stochastic differential equations because they're much easier to write down and analyze. We're going to look at the basic Euler-Maruyama method, and that generalizes perfectly straightforwardly to systems. So everything I write down for the scalar case, you can just think of them as vectors, and it will work for Euler-Maruyama. It doesn't work for higher order methods, but it works for Euler-Maruyama. So the scalar SDE, I tend to use capital letters for random variables and stochastic processes. So this is one way to write the SDE. You have a drift given by some function f, and a diffusion function given by g, and you have a Brownian process Wt, Brownian motion, and we're thinking of finite time solutions. So given the initial value or the initial state of the solution, and we're going up to some final time capital T. Okay. Now, as many of you will know, this doesn't really mean anything the way it's written. We have to regard this as representing an integral equation, because we can't differentiate in this world. We can integrate. So this is equivalent to the integral version, where we say that the change in the process is given by integrating. So we integrate and the new part here really is, how do we do this integral? How do we integrate with respect to Brownian motion? And it took a surprisingly long time for people to work this out. Until the 1950s, really, that Ito gave what's now regarded as the sensible, appropriate definition of how to add noise in this sense. And I should say there are many other ways to add noise to a differential equation. We seem to have somehow landed upon this one because it's got some neat properties. Most of the models that you see written down which involve stochastic difference equations, don't have any real justification. There are no laws of motion in the way that physics gives us differential equations. So that's one of my points I try to make to students, that sometimes we add noise because we know the model isn't correct, but it doesn't mean that adding the noise has made it any better. So just try to be aware of that when you're reading some of these pieces, some of these works. Okay, so that's the problem we're looking at. And if this makes no sense, don't worry, because the numerical method will converge to this. So the limit of the numerical method is the object that we're studying. Okay. Just as an aside, we're going to look at Euler-Maruyama, which generalizes Euler's method. As you might be aware, Euler wasn't doing numerical methods when the Euler method was first written down. The Euler method was used to prove uniqueness and existence and uniqueness of solutions. Okay, so writing down Euler's method isn't just something that numerical analysts do. It's one way to understand these objects. And in the same way for SDEs, you can write down Euler-Maruyama. It's essentially what's done in the theoretical world where they try to define and study these objects. Okay, so it's a perfectly sensible thing to look at. So this is based on discretizing. So everything here is on a finite time interval, 0 to capital T. We discretize it with steps of length delta T. We're going to use constant or fixed step sizes. At least 2 people in the room are interested in the case where the step sizes are not constant. That can be a very useful thing to do, but we'll focus on fixed delta T's. So given the initial condition, so we'll just take that, and then we compute these approximations. And by the time we've reached point Tn, we have this approximation xn, which approximates x at time Tn, is n steps along. And we can define Euler-Maruyama, maybe I'll use blue. So that would be Euler's method for an ODE, and then we just have to give that a kick. And delta Wn here is the increment in the Brownian motion. Delta Wn is the change in the Brownian process over that time step. And that's just normal with mean 0 and variance delta T. And if you sample that, you just have to take the square root of delta T multiplied by a standard Gaussian sample. So from a numerical analysis perspective, or from a simulation perspective, this is very straightforward. It's like simulating ODE. On every step, we give it a little kick. And that little kick is proportional to this given diffusion function at the current state. So this is the model gives us G, and the size of the kick is really what's its interest here. That's what you have to get right. It turns out that, so this is going to be, if we sample it, it's root delta T times normal naught 1. And this square root, finding if you haven't seen this before, it's the scaling that matters. The square root is the appropriate power. If you took a higher power of delta T, so you added less noise, then in the limit you have something smooth. If you took a smaller power, so you're adding more noise, in the limit you wouldn't get anything sensible. So this is the appropriate size of the kick, which gives you something different, something that's not differentiable, but turns out to be continuous. So that's really the essence of this, adding something of the appropriate size, giving it a kick. Another thing that students sometimes ask about is, these are stochastic processes and these are random variables. So this is an iteration involving random variables. When we do a path simulation, we're computing a sample. So we literally have numbers on the computer that gives us a trajectory. So we write this down often to mean the sample path that we've computed, but this is really the relationship between random variables. If you want to compare the exact solution with the numerical solution, at any point, you're comparing two random variables. So let's think about that. How do we compare them? Well, we can look at the weak error. Well, let's take a step outside. So the weak error is going to be the worst over all the time steps of, in this case, it's going to be the error in the means. So we compare the mean of the numerical solution with the mean of the exact solution. If you like, you can be a bit more general. For example, you could have moments. So you might want to have a test function like x squared. You might want to compare moments. This would be the corresponding moment of the true solution. But let's just stick with means for now. That would be weak. The corresponding strong error, instead of the error of the means, it's the mean of the error. So it is xn minus x of t. And this again is the sum. As I said, these are random variables, so they're infinite dimensional objects. So we can't just write down results that are independent of how you measure size. Norms are not equivalent in infinite dimensions. So these are different things. And under appropriate conditions, you can show that, sorry, that's the weak error. The weak error is order 1, so that behaves like delta t, and the strong error only behaves like delta t to the half. So there's a genuine difference between these two quantities in terms of how they behave. Of course, we'd like these to go to 0 as we put more work in, as we take delta t smaller. Yeah, this is well, I guess it's okay. This is okay. So we're letting delta t go to 0, but we're going as far as capital T. So we're taking more and more time steps as we take smaller and smaller delta t. And in that asymptotic limit, we get this behavior. And this is really the problem. Strong error, Euler-Maruyama only gives you order a half strong error. So if you want to get more digits accuracy in your solution, you have to do a lot more effort than you would with a first order method. Okay, this is how it differs from Euler. You might ask which of these is more important, weak error or strong error. No one seems to be able to give me a definitive answer when I ask them. It's certainly true that most things you do in life will require weak quantities. Anything you compute involving probabilities, means, variances, confidence intervals, those kinds of computations are weak. So the weak error arguably is the most important property. But there are some circumstances where you want a good strong error. And multi-level Monte Carlo is a way of getting more efficient weak approximations, but it does require, at least the original proofs required the strong error, the order of strong error to be involved in the analysis. So in a sense, they mix together in that way. You might ask, given that it's such a terrible method, its strong error is only a half, why do we use Euler-Maruyama? Anyone want to answer that question? Most people these days still use Euler Maruyama or similar low order. Anyone using Euler Maruyama wants to stand up for it?
It's super easy to implement.
Super easy, yeah. So it's cheap, yeah. And also getting higher order is not easy. That's the point, yeah. Even Milstein getting first order strong error in the very general system case gets complicated. You have to do these stochastic integrals. So there are simple structures where you can get higher order easily, but generically higher order is much more difficult to get. You have to put more effort in. Another point which often gets overlooked is that there's also a statistical error. If you're doing any sort of computation in this world, you'll probably compute lots of samples, average them together, and do some sort of Monte Carlo. So you're already buying in to that big statistical error. There's no point hammering the discretization error. You know, you don't want every sample to be almost perfect if you can't afford to compute many samples. Both those errors are important, and often it's statistical error that kills you. So you don't need high accuracy in some computations. So keep that in mind when you're thinking of using these methods. So my plan really is just to go through a simple sketch proof of strong convergence. As I said, weak error is probably more important, but the weak error analysis is totally different. It connects with PDE theory typically. So it's much more like a PDE proof, whereas the strong error result appeals to me as a numerical analyst because it looks much more like the kind of stuff I was taught as an undergraduate when I studied deterministic equations. Yes?
Is W a random variable?
Yes, W is a random variable, Brownian motion. So it changes by this amount. So from one time to the next time, the change in that process is just something that's normally distributed.
So should that be xn or?
Well, xn is the state, tn is the time. So this is how it's changed over time. It's independent of the state.
That changes in each simulation? Or?
Yes.
So there's no expectation.
There's no expectation here. That would give you a path. So these jiggity paths that you see, like stock market prices, one simulation will give you one path. Yeah. Yeah. Someone wants to chip in.
The expectation in the strong error is exactly over
Is
that.
that okay? That's what.
That's
related.
And you want the same Brownian motion to be used in the correct path and in the sampled path for the strong error.
But not for the weak error. Nobody has. Yeah. Okay. So as I said, the strong version, the strong proof is much more familiar to people like me with a deterministic background. So that's partly why I want to go through it. So I'm going to move on to the slides now. I should have said the PDF will be available if you want it. Just let me know. Also, I plan to take a 10-minute break because hearing my voice for 2 hours is too much even for me. So we'll have a 10-minute break between these two parts. Okay, so we're interested in this quantity. We're trying to show that that version of the error can be bounded by some constant times delta t to the half, a sufficiently small delta t, and that constant must be independent of delta t. It will depend on the time interval and depend on various features of the SDE, but won't depend on delta t. It typically gets much worse. It depends exponentially badly on the length of the time interval. So these are completely useless results if you're doing long time simulations. They apply over finite time. We're going to let Z be this the version of the error where we're now squaring. So this is rather than just the mean of the difference, this is the mean of the difference squared. So I'll just tell you a bit more about the notation. You can do this in discrete time, but I think it's neater to do it in continuous time. So we have to somehow interpolate the continuous solution. we've discretized step size delta t. Given x0, we imagine a process which stays constant and then jumps up to x1, and then changes to x2 and so on. So you might call that a step process. So it's a random variable, but the random variable stays the same over each increment of time. That's what we're calling x with a bar. So this allows us to build something that's continuous time, but represents our numerical solution. So over every time interval, we just stay with the same random variable. So define that. Just going back to the theoretical stuff, when you define things like these stochastic integrals, you typically do it for these simple step processes where it makes sense. You then say, given a more general process, we can represent that process as the limit of a sequence of these step processes. And then we say, okay, we'll define the integral for the general function by taking the limit of the integrals for the sequence of step processes. So it's a very similar thing that you do even just to define the integral as to what we're going to do to define convergence. In a sense, convergence is the same as proving a solution exists. It's very, very analogous. Okay. So here I'm now going over continuous time and comparing the step process with the exact value. If I can control that error, then of course this includes all the time points, Tn, on the grid. So that also controls the discrete error at those discrete time points. So this is a more general thing to try to prove. It will include proving strong convergence over grid points. We'd like to show that this version with the mean square behaves like delta t, because then by a magic result, which you might think of as Jensen's inequality, but I think in this context, it's actually Lyapunov. Down here. The expected value of this random variable x is bounded by the square root of the expected value of x squared. Okay, that's always true as long as those things I've written down make sense. You can generalize that to other convex functions, but that's the one we're using. So this is the right way round to do it. We can take square roots in this result, and that will give us delta t to the half for our basic strong convergence. Okay. It's very easy to get this wrong when you're doing analysis and think you proved something when actually you've used it the wrong way around. So watch out for that. So we can now start thinking about how to prove things. And we're going to use the Gromwall inequality. So this is something you may have seen in slightly different setting. There's a differential version. There's also a discrete version. We're going to use the integral version of Gromwall's inequality. So this is deterministic. If you have some, under appropriate conditions, some function depending on time, alpha of t, if you can bound it in this way, there are constants a and b. You can bound alpha by a plus b times the integral of alpha up to time t. Then you can deduce this inequality, that you can bound alpha by this exponentially growing quantity. And Gromwall is really the only thing we have going for us when we find this kind of proof. So everything tends to rely on some version of Gromwall's inequality. We're trying to control this squared error, the squared version of the strong error, z. So we'd like this constant a, we'd like it to scale with delta t. And we don't really care about this constant. That can be anything. That would give us our b. So if we can make A scale with delta t in this inequality, then we get the right behavior. Just go back and show you. We're trying to show that Z is bounded by a constant times delta t. We want to get some inequality for Z where first term scales with delta t and the second term integrates Z. That's the aim. I won't go into all the setup, but we're going to assume global Lipschitz conditions on F and G. So that just means for F, which is part of the SDE model we're given, you can bound the change in the F value by the change in the argument, and the same for G. And that has to be for all X and Y, for all real values X and Y. That has to hold. So it's global inequality, which is a huge assumption. Most models that you write down, especially non-linear models, will not satisfy global Lipschitz conditions. So this textbook analysis doesn't really apply to most models. There are convergence proofs which don't rely on global Lipschitz conditions, but they typically rely on some other quite strict property, some sort of dissipativity or one-sided Lipschitz type property. It's very difficult to generally prove that methods converge on nonlinear SDEs. And I'll give an example shortly. Once we've gone through this proof, I'll give an example showing what can go wrong with fairly simple models. And you may have come across this idea in applied maths that we can just assume assume solutions exist and are bounded because the physics, tells us if it's a physical model, if it makes sense, it must have bounded solutions. Well, that kind of thing doesn't really work here because there is no physics underlying it. And it turns out trajectories can go very far away from the origin. With small probability, bad things can happen, but a small probability is all it takes sometimes for the quantities to get out of control. So making those assumptions, they immediately imply these other conditions bounded linear growth. So as a function, when you square it, you have this quadratic type growth with some other constant L hat. So Lipschitz constant L and a linear growth constant L hat for the functions that define the SDE. You can then show that both the SDE and Euler-Maruyama have bounded first and second moments, but we're just going to assume that for this analysis. So assume these quantities are bounded over that interval. That's the setup. Okay, so now we dive in. So we're trying to control this difference, the numerical minus the exact, at some point S in the interval. And that point must live in one of the discretized intervals. So let that be in the interval between, say, TNS and TNS plus 1. It must lie somewhere. And therefore, you know which part of the step process we're on. Okay, so this is now the step process is constant on that interval, so it has that value x at the left-hand point, NS. We know that the exact solution has this integral representation, so we can expand that out in terms of the integrals. We can look at this difference here and say, well, we can regard that as the answer from a telescoping series, where we just take successive differences. So if you look at this sum of differences, all the terms cancel except the first and the last. So we get back here. So that's just an identity. And this is nice to do because this is how our method's defined. It tells us, numerical method tells us how to get from xi to xi plus 1 by simply adding the increments. So this summation now can be written this way, where we're just applying Euler-Maruyama, and we're comparing it with what the exact solution propagates like. You can also interpret this differently. This is like a Riemann sum approximation to these integrals. So Euler-Maruyama is essentially doing Riemann sums. And we're looking at how much error we create when we do that. Okay. But notice that we're summing up to, we're only going as far as NS here. So the solution, the Euler-Maruyama essentially stays constant over that interval, whereas the true solution changes. So that's going to come into this analysis. Okay, so let's look at those terms. We go back again. We can think of those sums as integrals. So integrating f of the step process, that's constant over that time interval. So that Riemann sum just becomes delta t fxi, and the same for the stochastic version as a change in the Brownian path. So I can replace those sums, go back and show you. I can replace those sums by the corresponding integrals of the step process. So now integrate the step process and take off what the true solution does. But you have to keep in mind that because of the way we've defined the step process, we're only going as far as TNS here. We're not going as far as S, because we've essentially pretended the solution's constant over this bit of interval. So we're not taking account for what the exact solution is doing over that tiny extra bit of time. That's going to cost us. So when we compare these integrals, we can pull them together up to time TNS, and then there'll be a bit left over from TNS to S in these second sets of integrals. Okay, so the first integrals involve differences of numerical and exact over that time interval, and what's left over, these little bits of integral, just involving the exact solution. Okay, now let's just take a step back. This is really a consequence of the fact we define step processes. You could define a more complicated interpolant if you like. You don't have to just use constant interpolants. You could take X, take your numerical method at 2 time points, do anything you like in between. Anything you like is fine as long as it interpolates. It turns out this result is going to be sharp. So whatever you do instead is not going to get around the fact that it's delta t to the half that comes out at the end. So we haven't done anything too crude. What we get at the end is still going to be a sharp result. So we can't get around this difference in a sense, this extra bit. Okay, so we have these 4 integrals, and this is a classic trick in analysis. We want to look at the squares of the error. If you have 4 things added together and squared, turns out you can bound that by 4 times the individual squares. Probably isn't too surprising. The fact that it's 4 doesn't really matter for us. It's just going to be a constant. That turns out to be the best constant. So just going back, we have these integrals. We're going to square these 4 separate quantities, add them together, and then take expectation. So that's all allowed. So we now have some way of bounding this error that we're trying to control. And now we've got it in terms of 4 integrals. 2 of the integrals involve differences of f and g, where we compare the exact and numerical solutions. So thinking ahead, it's the Lipschitz constant that's going to come in. We can then convert that into differences just between S to the next bar, up to a constant. And these two integrals just involve little bits of time. So it's the fact that there's short integration periods that's going to allow us to control the size of those two. Okay, so let's bound those four terms. So that's the first two. So this is Cauchy-Schwarz is going to come in. I'll explain that a bit more. From a linear algebra perspective, if you've got two vectors A and B, then A transpose B can be bounded by 2 norm of A times the 2 norm of B, or you can square that if you like. Okay, so that's probably familiar to people. There's an integral version in this world where if you've got two integrands, say A of S and B of S, given by stochastic processes, you square and take expectations, then you can bound that by the product of the expectation of the product. Guess I should use an R there. Okay, so that would be an application of Cauchy-Schwarz in this setting, but we can also just take AR be density equal to 1, and that allows us just to bound the integral of PR all squared, an expectation. And integrating 1 from 0 to S just gives us the size of the interval S. Take the expectation inside, and you get the expected value. PR squared dr. So we're allowed to exchange expectations and integrals freely this morning. So that's what we're doing here, taking that difference, regarding it as being times by 1, pulling out the time interval, and being left with that expectation. Then the Lipschitz constant says differences in F's can be bounded by L times differences in the arguments, because we're squaring it's L squared. This T and S doesn't go any further than capital T, so we can just crudely bound that by capital T, and we're left with this quantity. If you think back to Grunwald, this is all we need. We just need some constant times the integral of the thing we're trying to bound. So that's perfectly okay for Grunwald. And the second term that we had, so this is actually the third term in the expression. Oops, wrong way around. This third term is a similar quantity. Again, pull out the time interval. This time it's just S minus T and S. That's bounded by delta T. That's no bigger than 1 time interval. We now use the linear growth condition, so we can bound that by some constant times. That's second moment term, and that's just some constant times delta T squared. So that's going to be good for Grunwald. That's the A in the Grunwald inequality. Okay. And don't forget, we're assuming that these second moments are bounded. So that's 2 of the 4 terms dealt with. What about the stochastic integrals? So if we go back, there's a a stochastic integral here and one here. We have to do a bit more with those. So there's something called the Ito isometry. And the Ito isometry allows us to go from stochastic to deterministic integrals. One version tells you that the expected value of the integral of some process is just the expected value that quantity. And again, if we swap these the expectation and the integral, that's just integrating the second moment. So all these things are really, they might look a bit messy, but if you just think of step processes, it's actually fairly easy to convince yourself these are true, and that's the way it's mentioned in the book. So it might look a bit daunting, but you can actually justify this just by Riemann sum type arguments. The great thing about this is if we go from a stochastic integral to a deterministic, and once we're in the deterministic world, then we're much happier and we have standard techniques to use. So that's what's happening in this first case. And then we use Lipschitz to difference of the G's becomes Lipschitz times difference in the arguments. So that's our second version of the constant B that we needed in Gromwall. And for this one, we then get something where we pull out the size of the integral length and we get a delta t. Yep. Sorry, what's the H is a stochastic process. Yeah. Okay. Because our solution here, our solution and the numerical method are stochastic processes now. Okay. Now it turns out this is the bit that goes wrong in the sense of not getting the desired first order. We've had to just use the length of that interval, pull it out, and get delta t. Whereas if you look at the deterministic version, we managed to get a delta t squared. So nothing's gone wrong. It's just that's what happens when you do this. You get the delta t. If I go back to Gromwall, that's where my delta t comes from, not delta t squared. So up here, I get a delta t, not a delta t squared. When I do Lyapunov or Jensen's, I get delta t to the half. That's the only bit that's cost us the order. So that then goes together, gives us the proof. So as I said earlier, that is the sharp rate. You can't do better than delta t to the half. Strong convergence of Euler-Maruyama. It's only that dw integral at the end, which cost us the order half, which makes sense because we know that standard Euler on a deterministic problem has order 1. So if we throw away the noise, set g equal to 0, if we didn't have those stochastic integrals, we definitely get order delta t. So it makes sense that it's only the stochastic integral bit that cause things to go wrong. In terms of the definitions, if you have strong convergence, so if the strong error tends to 0, then the weak error is bounded by the strong error. So the weak error will also tend to 0. So indirectly, we have proved weak convergence of Euler-Maruyama, but we've proved it with order a half when the sharp version gives you order 1. So you can't get a good result simply by saying that strong implies weak. If you want to get the optimal weak order of convergence, you have to do a different proof technique to get the sharp version. Okay. So I promised a little bit more about what can go wrong just before we finish this first section. So this is a cautionary tale. This is now a simple deterministic ODE. We're going to make it stochastic shortly, but it's a deterministic ODE. It's a gradient system. It has potential x to the 4 over 4. So this is the derivative. dx by dt is minus x cubed. So if x is positive, the derivative is negative, taking you towards the origin. If x is negative, the derivative is positive, taking you towards the origin. So all solutions tend to 0. It's a dissipative ODE. So it's perfectly well defined ODE. What happens if we discretize it with simple Euler method? Well, there's Euler. That will converge if you choose delta t small enough with a fixed initial condition. But let's think of it slightly differently. Suppose delta t is less than 1, and suppose the initial condition scales like delta t inverse. So someone's given you a delta t, but then they've given you an initial condition that's roughly proportional to 1 over delta t. So this is what Euler does on the first step. xn, x0, that's delta t to the minus 1. Delta t times x cubed is now delta t times x to the minus 3. So that reduces to delta t to the minus 2. So we've got this size, and we've got a minus sign. That's our first value after one step. If you've got delta t to the minus 2, then Euler on the next step gives you that. Then minus delta t x cubed gives you minus delta t times x times minus delta t to the minus 6. So you get plus delta t to the minus 5. So this is starting to go crazy. And then once you plug that into the next step, you get a minus and a delta t to the minus 14. So these numbers are oscillating and getting much bigger in size. This is under the assumption that having chosen a small step size, a nasty person gives you a really, really large initial condition. Okay, so we can't really control what's going on if the initial condition is out of our control. Okay, so that's the non-linearity mixing with the explicit nature of Euler. And you can say, well, this isn't a problem in the deterministic setting because we're normally given a problem. Here's my ODE, here's my initial condition, and then there'll be a sufficiently small delta t, which gives you convergence. So there'll be 0 to delta t star. In that range, everything's fine. But in the stochastic setting, it's not so simple. So let's just add 1 times dw, so the diffusion coefficient is constant, equal to 1. And then here's the corresponding Euler-Maruyama. It's just Euler with a Gaussian kick, scaling like delta t to the half. And here's the issue: that delta Wn is Gaussian, so it has an infinite support. There's a very tiny chance that you get a big number. When you ask your computer for a Gaussian sample, there's a very tiny chance it gives you some ridiculously large or small number. Okay, so there's a very tiny chance that you get into this regime where Euler can no longer cope with the nonlinearity and you get this growth. It only takes one bad example, one bad delta W along that trajectory, and you're suddenly in this world where things start to blow up. Now that's a very low probability event, but once it happens, it's incredibly bad. So one way of saying it is it's an exponentially small event, but it's double exponentially bad when it happens in terms of the growth that gets created. And overall, when you take expectations, it's so bad that when you multiply the badness by the probability, it blows up the expectation. So this incredibly unlikely event is so dramatically bad that overall it messes up the expectation. So you can show rigorously that the method does not converge in this weak or strong sense. on this very, very simple additive noise SDE
With constant steps.
with any constant, yes, yeah. Now, that sounds terrible because there's ways around this. You can, there's lots of papers looking at this ODE, this SDE and similar versions. Fixed step sizes, you could argue, is not good. So you could vary the step size, but even simpler, you could just throw away the bad trajectories. You could pick a big number L and throw away any trajectory that exceeds L and let L go to infinity with delta T or something, and you'd be able to prove that process converges. Or you could replace your Gaussian sampler with something that's truncated. So don't let the random number generator give you huge numbers, and make that truncation depend on delta T. So you know, to get some accuracy out of it, so you can then prove that under those circumstances you can get convergence. So no, it's not such a big deal in practice, but just theoretically, we can't say we have strong convergence of Euler Maruyama on that ODE. So that's that SDE. So you got to be careful how you phrase things, but in practice, just throw away stuff that looks bad, and typically your estimates will still be fine. Your Monte Carlo estimates will still be okay. Right. So I think that's the end. Oh no, there's one more little bit. One reason why strong convergence is regarded as a useful property is because it means when you compute a path, that path that you compute, given the same Brownian motion, stays close to the path followed by the exact solution. So strong convergence implies pathwise convergence. Given a Brownian path, if you use the increments of that path for Euler and look at the true solution along that path, those two things stay together. And that's because of the Markov inequality. So we have this result, which is strong convergence. Markov, which I'll write down generally, if you like. Markov says the probability that, say, non-negative random variable exceeds any value you like, A, can be bounded by the expected value of that random variable divided by A. So it's a very general, as long as those things make sense, it's true, very general result. Of course, it's not sharp for a typical X, but it's true. So we're now thinking of X as being our error, and we can take A to be delta T to the quarter, and then that expectation bounded by K times delta T to the half, and we're dividing it by A, takes us down to delta T to the quarter. So we've chosen a quarter to balance that ratio. So this is telling us the chance of the error exceeding some small number is bounded by some small number. So in this sense, we're staying close to the exact solution path with high probability. Or if you take the complement, then the chance of the error being small along the trajectory is close to 1. Now, when I say small, this is a terrible power. Delta T to the quarter is pretty rubbish. But at least it's telling us something, that if you're prepared to take really small time steps, then in a sense you can justify your trajectory. The one that you plot on your computer is close to a trajectory of the exact solution. Okay, so that's one consequence of strong convergence, which I think is what people think of when they talk about strong convergence. Okay. So I suggest we have a 10-minute break. It's just 11 o'clock now, so we'll come back. If you want to come back at 10 past 11, and we'll do a bit on linear stability. And feel free to ask questions either now or during the session.
Yeah, a little bit. Something
I wish I had these slides when I started.
All right, okay, yeah.
It would make learning.
You want to buy the book, you know, you can always buy the book, go to the library.
我还没打过扑克。上面这个加号一起做那个上次那个。那个也大。
Right, so this is part two. Probably won't be as long as part one. This is looking at linear stability. So it's a topic that I looked at many years ago, which I thought was interesting and still seems to be relevant. I'll just give a little bit of background in the ODE setting, which you probably come across in undergraduate lectures. In the deterministic case, we're obsessed with this linear test problem, where scalar lambdas are constant. Sometimes we're adventurous and allow lambda to be complex, and sometimes we only care about real. But it's a simplest possible ODE that's not completely trivial. The solution is just an exponential. But this is useful partly because you can take a non-linear ODE, and at least close to a fixed point, you can linearize it. So solutions behave like a linear problem. You can then diagonalize it, so the system behaves like an independent, uncoupled set of scalar linear problems. So asking for good behavior on this type of simple system often transforms into good behavior in more general settings. Moreover, we're really concerned with errors. So if you're close to the exact solution and you make a little error, how does that error propagate? Well, at least locally, you can linearize. So although we think of this as a model for the solution, you can also think of it as a model for the error. And if you linearize, you'll find applying the method to a linear test problem gives you some insight into how the error in the method might propagate over time. So that's really why there's been so much research on this seemingly simple looking test problem. We really do care how methods perform on this simple problem. Once you allow lambda to be complex, there's a whole world of complex analysis comes in, looking at things like Runge-Kutta stability regions. There's lots of nice maths comes in as well. Okay. So what happens when we apply Euler? Then we're just propagating with this amplification factor, 1 plus h lambda. So if we want stability, say lambda has negative real part, we want this factor to be less than 1 in modulus. So that would be our stability condition. So given lambda, you choose h such that this is true, and then you guarantee that the yn tends to 0. And if lambda is complex, then that turns out to be a condition that requires h lambda to be in that unit disk. So here's imaginary lambda and real lambda. So if someone gave you a value of lambda, you have to multiply it by h. Multiplying by h takes it on what should be a straight line towards the origin. And once you're inside the disk, then you're stable. So h has to control lambda in that way. If you're only in the case of real, then we'd say the stability interval is -2 to 0. So if somebody gave you a large negative lambda, you have to scale it by h till it lives in that interval. Okay. Just out of interest, implicit Euler would be yn plus 1 is 1 plus. Well, once you rearrange, you get 1 minus h lambda on the bottom. And that's a good property that the exterior of that disk. So the entire left half of the complex plane is stable, so there's no restriction on h. If you have a negative real part lambda, then this will always give you a stable result. Or the stability interval is the whole left half of the real axis, but also you'd rather not have to the right of 2. Okay, so this is the implicit version giving you better stability. Okay, another point, well, just to try and motivate what we're doing next, we're going to look at this SDE, which is scalar and has these 2 multiplicative terms. So mu x, so mu is like lambda, and we also put a multiplicative diffusion. And I'm only going to look at real values of mu and lambda. And just to explain why we're not quite as generic here, if you had, so for the ODE, as I said, you could have a vector version where y prime is, say, b times y, where b is a matrix, a linear constant coefficient ODE, and you could, under reasonable conditions, you can diagonalize. That makes the eigenvalues of b. So lambda here represents an eigenvalue of b. But in the SDE case, if you wanted to do the system version, it would be something like ax dt. Maybe you want to still a scalar Brownian motion. You can have a matrix B times x, where x is vector valued. But the problem is you can't simultaneously diagonalize 2 matrices with the same similarity transformation. You get the same problem arises for second order ODEs, and those methods, the stability analysis isn't really justified as nicely. So the same thing happens here in SDEs. Once you have 2 matrices, you can't pretend that the scalar problem captures everything about that world of systems, because you'd have to be able to simultaneously diagonalize both A and B with the same transformation in order to reduce it to uncoupled scalar. So we're going to look at this scalar linear problem, but keep in mind it's not quite as easy to justify it as it is in the ODE case, right? And someone asked a question about time-dependent SDEs. I guess we're going to see a lot in the diffusion modeling context. We're going to see a lot of versions of this type of problem where mu and sigma depend on time. So that's another generalization you could look at. I'm not aware of much analysis of stability, those types of problem. Right, so that's what we're deciding to look at. An SDE where someone's given us scalars, real valued scalars, mu and sigma, and we study this linear SDE and the corresponding Euler-Maruyama version, hoping to get some insight into stability. This is such a simple problem that we can solve it exactly. So that SDE has this solution at the top, this exponential behavior. Now, this is unusual and sometimes misleading, because the solution there just has this nice property that the solution at time t only depends on the Brownian motion at time t. Only w of t appears in that expression. That's not generic. Normally the solution depends on the whole of the Brownian path up to and including time t. So this is a very simple SDE, doesn't capture everything about more general cases, but you can just think of this noise term just somehow affects the exponent in the exponential. And it's then very easy to study for example, the second moment. So the true solution, x of t, its second moment evolves like e to the power 2 mu plus sigma squared times t. So sigma is the size of the noise we're adding, and that affects the second moment in that way. It has to be sigma squared, because if you had a minus sigma, it would still essentially be the same. The Brownian motion is symmetric, so minus sigma should be the same as sigma, so it has to be that property. So this is the exponential rate of increase or decay. So completely straightforwardly, if you want this second moment to tend to 0 with time, you simply want this exponent to be negative. So dividing by 2, this is the condition which characterizes what we call mean square stability for that linear SDE. If you take away the noise, set sigma to 0, we're back to the ODE case, and thankfully we get the right answer that mu must be negative. You might also recognize this model as the asset price model in the Black-Scholes equation. So we're regarding it as a test problem, but in finance, it's the simplest model of asset price behavior that was introduced by Black-Scholes and others. Okay, that's one type of long-term behavior, but there's another type which is equally relevant, I think, which is just, does the solution tend to 0? So as time goes to infinity, does this happen with probability 1? Does every trajectory, does a given trajectory with probability 1 tend to 0? And that turns out to have a different characterization, because the Brownian path, W of t, essentially behaves like the square root of delta t. The size of W as time increases grows like the square root, whereas the first term here grows linearly. So if you have a negative mu minus half sigma squared, as long as that's negative, it will beat out the Brownian motion contribution. So all you need for asymptotic stability is the first part, the mu minus a half sigma squared, be negative. Okay, so it's a different condition. But again, if you throw away the noise, you still get the right answer that mu must be negative. So it turns out adding the noise actually helps in terms of having this asymptotic stability property. It's hard sometimes to understand, but that's what happens. So this condition, of course, is more difficult to achieve than this one. So mean square stability will imply asymptotic stability, but that's not true in general for stochastic processes. So don't be misled by this example again. In this particular case, we have this implication, but that's not always the case. And there are complicated books on stochastic processes with these diagrams telling you what type of stability either is or isn't equivalent to what other type of stability. And this is by no means easy or straightforward to get all that into one page. So we have this property here, but it's not true in general. So we're going to ask, how can we reproduce this behavior with Euler-Maruyama? In particular, what step size restrictions we'll look at. In fact, we're going to do something a bit more general. We're going to allow implicitness, but only in the deterministic part of the method. So given a parameter value theta, then here's the definition of the stochastic theta method. If you throw away the noise, forget about the final term, theta equals 0 would be Euler, theta equals 1 would be implicit Euler, and theta equals a half would be what's called the trapezoidal rule. So we're allowing ourselves to be implicit in the deterministic, the drift part. We're not doing the same thing in the diffusion term. In principle, you might think, well, let's have g of xn plus 1 in there and make it fully implicit. That might give us even better stability just based on deterministic results. It turns out that's not a good idea. Even the expectation of the numerical solution might not exist if you start allowing implicitness in the diffusion term. So mentioned in the book in more detail, but it's very dangerous to be fully implicit in that sense. So we're only going to allow implicitness in the drift. If f was a non-linear function, we'd have to solve that non-linear equation to find the next value. That's why it's implicit. Because f is linear, in our setting, it's actually trivial just to rearrange and find an expression for xn plus 1. So that's the method. Okay, so let's first of all look at mean square stability. So going back, mean square stability means you square the process, take its mean, and look at long time behavior. Do that for the method. Well, let's go back. Here's the method again. It depends on this parameter theta. F is now linear, G is linear. So we can just rearrange. That's the iteration satisfied by the stochastic theta method on the linear equation. I've written the increments, the delta W's, I've written them as root delta T times the standard Gaussians. That's going to be a bit more convenient. I've got the parameters mu and sigma from the diffusion and the drift. So this is actually straightforward to analyze. It's just a simple linear recurrence. We want to know how the solution behaves when we square it. So let's square it, and then take expectations, just collect terms together, get that simple expression. Using the fact that expectation is a linear operator, so we can take expectations within a sum, and using the fact that the increments of the Brownian path are independent of the numerical solution at time tn. So some of the cross terms, when you square, some of the cross terms vanish when you take expectation. So everything simplifies very neatly. If this factor is not equal to 0, and that will be true if delta t is small enough and you have a stable problem, then we can divide through. So we get this simple recurrence, simple one-step recurrence for the way that the mean square solution, numerical solution, is behaving. Okay. So stability simply reduces to this amplification factor being less than 1 in modulus. It's not negative, so stability means this factor less than 1. So it's a nice, simple, easy to understand relation. So mean square stability is this factor less than 1. And you can rearrange that inequality, and what you find is that it reduces to this inequality. So you've got the step size, you've got your parameter theta in the method, and sigma and mu are the diffusion and drift coefficients of the SDE. We tried to do something analogous to this ODE world. We want to draw pictures and talk about stability regions. And it's useful to think of these parameters. So let x be the drift coefficient scaled by delta t, and let y be the diffusion coefficient squared scaled by delta t. That means if you multiply through by delta t in that inequality, then it reduces to this expression. Okay, just multiply through delta t, rearrange, then that's the expression for the stochastic theta method to be stable. This is the corresponding expression for the SDE. If you multiply through by delta t again, you get something that looks very similar. So we can now, in a picture, compare these two. This is a parabola in the xy plane. I hope we can notice. It's either a happy parabola or a sad parabola, depending on theta. So as theta passes through a half, the nature of the parabola changes. So that's going to actually dramatically change the region in which we have stability. So I'll just pop up those values. So x is tu, little x. Y is delta t sigma squared. So the SDE is stable. And u plus a half sigma squared is negative. So that means x plus a half y is negative. Or if you rearrange x less than y less or equal to minus 2x. Right? So here are the corresponding pictures. This is not the complex plane because we've had to restrict ourselves to real values. We've got two parameters now. We've got a drift and a diffusion parameter, but they're real valued. So the two axes are drift and diffusion. X is drift scaled by delta t. Y is sigma squared, diffusion value scaled by delta t. The region where the SDE is stable is where y is less than minus 2x. So the wedge, which goes off infinitely, the wedge based on slope minus 2 through the origin, that whole region is where the SDE is mean square stable. This little parabola is now defining the region where Euler's method, theta equals 0, Euler-Maruyama, is stable. Okay, just the underneath the tip of this parabola. I go back. That's the parabola. Okay, so given coefficients, and also there's a corresponding negative, but we can think of sigma as being positive, so sigma squared is positive. So given values, mu sigma squared, then the step size has to be chosen so that along this ray towards the origin, you're taken into the Euler-Maruyama region. It's the same idea as in the deterministic case. It puts a restraint on the step size. There's a finite region of stability in which we're stable, given a stable SDE. Also, it's quite nice that given an unstable SDE, this method is always unstable. There's no step size which you can get a stable computation. So it respects instability, and for sufficiently small h, it will guarantee stability. As theta increases, so we're now going to implicit methods. If you let theta be a quarter, then this parabola grows. Still unhappy, but it grows. So there's now a bigger region, and a larger choice of step sizes will give you stability. Once theta equals a half, if you go back, when theta equals a half, this term disappears and we get the exact reproduction of the SDE stability. So this parabola grows and grows. When theta equals a half, it flips into just being the wedge and completely reproduces the stability of the SDE. When theta gets bigger than a half, it's trying too hard now. It's overstable, and we get this happy parabola, which always meets the origin. So underneath this arc of the parabola is where the method is stable, and it includes the wedge. So given a stable SDE, there's no restriction on the step size for the method, but there's also a region where the method has this extra stability, which we shouldn't really have. And there's also this bit out here where the parabola reappears, where you have a little bit of stability, which shouldn't be there. When theta equals 1, you still get similar behavior. Okay, so it's a nice story you can tell, which generalizes in a fairly intuitive way the corresponding pictures for the ODE case. So that's mean square stability. If I go back, I said that asymptotic stability is also equally reasonable to ask for. If the method has, if the problem is asymptotically stable, under what conditions is the method going to be stable? Okay. So I think here it's better just to write down the general form of the theta method. In a sense, it's a randomized geometric progression. So the value on the next step is some factor times the value on the previous step, but that factor has a deterministic part, let's call it A, and a random part, which involves a Gaussian Vn. So it's a sort of randomized version of a geometric sequence that we're generating. Here's A and B in terms of the parameters introduced. So how does this type of randomized geometric sequence behave? What do the trajectories do? Well, just take modulus, and we get this expression. And in this world, statistics and probability, whenever you see a product, the first thing you tend to do is take logs, because we'd rather work with sums than products. So if we take logs in this expression, the log of this modulus now becomes the log of the initial condition plus the sum of the logs of these random variables. And we have lots of results about sums of random variables that we can appeal to. So it's a much easier world to live in than the world of products. We'd like this to go to 0, this quantity xn. So we'd like the log to go to minus infinity. This first term doesn't depend on n. So intuitively, we'd like these logs. Remember, the v's are all the same distribution. So we'd like the log, like the contribution from each of these terms somehow to tend us to minus infinity. So I want these things in some sense to be negative. And that can be made rigorous using appropriate probability theory. And you can show that it's the expectation that matters. So you get this property of asymptotic stability if each of those terms in expectation. It's the same quantity because these are identically distributed. So if the expectation of the log of A plus B times standard Gaussian is negative, then you'll have a process which with probability 1 tends to 0 as n goes to infinity. Just to remind you, the A and B there depend on the parameters in the method and delta t. So this characterizes asymptotic stability of stochastic theta method. And it looks neat. And when I was first doing this, I showed it to a colleague and he said, oh yes, you can understand this in terms of Meyer's G function. This is what you've written down there is an example of Meyer's G function. You look at Meyer's G function and it's just defined to be this quantity. So giving it a name doesn't really help you do any analysis. I wanted to know some sort of explicit characterization under which this holds. But it seems like there's no simple way of progressing other than just evaluating the corresponding integral to see whether the expectation is negative. Okay. So it's a neat way of writing it, but it doesn't really give you any benefit in terms of understanding things like regions of stability. You just have to compute them. Okay, so in the theta equals 1 case, remember we have a minus sign here, so we have a plus sign there for asymptotic stability. So asymptotic stability happens when y is above 2x. Remember, x involves the drift, y involves the diffusion. So anything above this straight line or to the left is asymptotically stable for the SDE. And it turns out the numerical method, when theta's 1, is stable inside these two bulges, which we just computed numerically based on that characterization. I don't have an analytical expression for these. So if you take a drift and diffusion coefficient here, you have to pull the step size down towards the origin until you're inside this bump. If you're out here, then any step size will work. Here's a region where you have stability, then you lose it, and then you get it back again. Not even monotone. You know, if you're out here, you can suddenly lose stability, get it back again. Here, you're stable, then you become unstable, and the problem itself is unstable. So you can get various combinations of behavior. You'll always be stable for small h just by consistency. Around here, the region has to match the slope of the wedge. You'll always be stable for sufficiently small h given mu and sigma. So that's always worth checking when you're doing these pictures. Okay, so that's theta equals 1. And just to wrap up, here's an example, tries to put everything together. This is theta equals 0. This is Euler-Maruyama, the explicit method. Remember, the SDE is mean square stable below this wedge, y is minus 2x. It's asymptotically stable above this line, y equals 2x, and to the left. It turns out that it's mean square, well, we know it's mean square stable below this, Euler-Maruyama's mean square stable below this parabola. And the asymptotic region turns out to be this, like an egg-shaped region. So anything inside the blue, but that value of delta t gives you a stable mean square SDE. So I've got to show examples where mu and sigma are up here, and I take smaller step size, and also where mu and sigma are here, and I take smaller step sizes. Because it's interesting just to think what's happening here. We have a computation which is asymptotically stable. So every trajectory we compute tends to 0, but it's not mean square stable. Every individual trajectory with probability 1 tends to 0 as time goes to infinity, but in mean square, the expected value of that process goes to infinity. Time goes to infinity. Okay. It took me a while to even believe this could happen, and then when you do the computations, you can sort of get a feel for it. So I'll show you trajectories from these different steps. Okay, so the top picture there is the -3√3 case. So -3√3. So we're starting here, taking this step size, where the SDE is mean square stable. The method is not. When you come into here, the method becomes asymptotically stable with this step size, and then it becomes all, both of them, asymptotic and mean square. These are the corresponding trajectories that you see. So this just blows up. This is 10 to the 20, it's a huge number. This one gets pretty big. Delta t is a half. Just remind ourselves. This is where we have asymptotic but not mean square. Then this one is asymptotic and mean square. And here's the other case, mu is a half and sigma's 1/6. So we're up here. So this is asymptotically stable. So this is neither for the method, then it's neither, and then it becomes asymptotically. So you can get a bit of an understanding by computing trajectories. But roughly speaking, if it's asymptotically stable but not mean square stable, that means if you're sitting on any trajectory, you'll eventually go to 0. But if you pick any time, you'll see some bad trajectories. No matter what time you pick far in the future, there will be some bad trajectories which cause the mean square to be large. But if you fix a path and just follow that path over all time, it has to go to 0. There's always some bad paths, but it's not going to be the one that you pick. And that's sort of my understanding of it. Those two things can go together, but it's a weird thing to try and think about. But you can see it happening. You can see, this is, you can just see from the trajectories that sort of thing is what's happening. Eventually, it has to go to 0, even though the mean square version of it has to blow up. Okay, so that's all I wanted to cover this morning. I'm happy to hang around, answer any questions. Feel free to buy the textbook if you're interested. If you want the PDFs, just let me know and I'll distribute those. Okay, thanks for your attention.
Okay. So, hello everyone. I'm James. I'm one of the organisers. I think about now there's meant to be foods. I don't know. I'm seeing a nod. So hopefully we can all leave and then enjoy the food. And then hopefully see you this afternoon for more mini courses.
Sorry.
他之前一直不在做吗？而且最近让他们搞之后，开始研究提升 model 的 numerical the ability parts。他不是这么 Magnix 新招了一个中国人，就是在跟他做这个。小 Kevin 是这样，你在
So list online, then you get emails asking you.
Oh, okay.